My name is Richard Socher. I'm the chief scientist at Salesforce. That means I wear a lot of different hats. I basically lead the research team, where we have both an applied group and a pure research group. In this talk, I'll focus a lot more on one exemplary project that we work on in the pure research group, namely what I think is a pretty important part of the future of AI as we're trying to generalize it more and make it more powerful, and that is multitask learning. But I just wanted to say a little bit about the applied research that we do in the group as well before I dive into this in-depth project. And so basically on the applied side, we work in natural language processing, computer vision, recommendations, and speech recognition in terms of the actual applications that we work on, or sort of modalities. And in terms of the techniques, we're mostly focused on deep learning and reinforcement learning. And you can dive deeper into all of these. In speech recognition, we try to be very robust. We also try to make it easy to configure your own speech system very, very quickly to make it better for your particular company use case. And recommendation engines, we integrate and work with Commerce Cloud. We're actually one of the largest e-commerce platforms at Salesforce too, which very few people know because nobody goes to salesforce.com to buy anything, but they go to adidas.com and Macy's.com and companies and websites like that are all powered on the Salesforce platform. And we also work with, in terms of the real applications, in terms of industry clouds, or just applications for companies, work in sales, but also actually service a lot. And we're also the largest provider of marketing software. So if you want to understand your social media presence, your media campaign, and things like that, usually use Salesforce for that. So across all of those areas, we help with a bunch of different applications and the technology behind them. So with that, I'm going to start looking into one of the research projects. Our research team can work on applied things, but a lot of us in the team are also just excited about pure research applications to push the state of the art forward. And then with the applied research team and engineering, we actually try to make it widely accessible. That is sort of our vision. Push the state of the art in AI forward and make it widely accessible. So with that, I'm going to start sharing my screen. So welcome to my talk on the Natural Language Decathlon. And the big focus area here is multitask learning. And the NLP Decathlon is the data set that we use, and the framework in which we cast multitask learning, make it intuitive, easy to use for people, easy to extend, and easy to understand is question answering. This is not just my work. I've actually have the fortune and luck to work with some phenomenal people here at Salesforce Research. The first author of this paper is Brian McCann, and you really have to appreciate his endurance and grit and ability to push through some hard times, because this project is something that I've been wanting to do for several years, but it requires a lot of engineering before you can get to the interesting AI bits, and very few people were willing to go through that, but Brian showed and persevered through this and really built the whole thing, and it's all on GitHub. You can look at all the code and pre-processing and everything. Nitish also helped a lot in optimization and really making the performance better. And Saming Hyung is one of our directors here at Salesforce Research, and he is really involved in pretty much all our projects and is helpful on everything. So really phenomenal team that has been working on this. And one of the ways we're thinking about, what does it mean to push the state of the art in AI forward? And sometimes if you want to understand how to move forward in the future, it's good to look also into the past and see what has actually been really impactful, which ideas have kind of really made progress in the field. And to me, the way I see the last maybe decade or so of immense progress in AI, and in particular also in natural language processing, which is the field that I really started in 2010, we saw this shift from machine learning with human design features, where in NLP we had linguists and had experts morphology and things like that, syntax, grammar theory, and different aspects of language. And we're still using some of those ideas, but we're trying to automate more and more. And deep learning in 2010, I had my first deep learning for NLP paper. We really wanted to replace some of the manual feature engineering and use deep learning for feature learning. So you take raw input and you try to learn everything from that raw input to the output that you care about. So for instance, in translation, you just have an input sequence and output sequence. You try to learn all the potentially interesting layers in between automatically. And that took a while for the community to really pick up. Word vectors helped a lot. GLOV and Word2Vec helped a lot of people appreciate that words might not be these discrete units, but have a continuous vector representation. And now what I think we're currently seeing is that we do deep architecture engineering for single tasks. So people know, oh, I want to do question answering on the Stanford question answering dataset squad. And so they come up with very particular architectures that can copy a span over, and they're focusing more and more on that particular architecture. But then in some ways, we're now in a similar stage to where we were before, in that we're still engineering now not the features, but the architectures for each particular task. And to me, that will not really allow us to push forward in a really fundamental way. And in fact, I feel like we're sometimes a little bit like this dog here, in that we keep restarting from random every time we start these new projects. And it's clear that if we were to teach a new skill, and every time we're done teaching it a new skill, we ask it to forget it first and then restart from random, we'll never get to more general AI. So we really need to push forward this continuous learning in a way that will allow for transfer and other things. So basically, I don't want to diss the amazing progress that we've made as a field, right? It's been phenomenal. We've gotten great performance improvements in recent years when we take a specific data set, a specific task, tune a model and architecture for it, and then hill climb on this metric. And when we see new results, getting better performance on a data set where the data set is larger than maybe 1,000 times the number of classes that you have. So in ImageNet, for instance, we have 1,000 pictures per visual category that you want to classify. And sure enough, like an ImageNet is one of the first breakthroughs with large neural nets and enough training data, we can do it. If you want to do machine translation, then in some ways each word is a class. So you need maybe a couple millions of examples of words, and then you translate quite well. And because language usually has some power law or Zipfian law, so some words are quite rare and not very common. You basically do worse and worse in some of those. So, and of course, there's the complexity of the sequence. It's not an independent thing, but I think roughly we can do quite well in those regimes. But again, this is not going to lead us to having a single model that can just understand language, even though it wasn't particularly trained on that exact metric or task. But it's seen similar things like it, and that's kind of what the goal is. And so on another high level, we also, in almost all cases, start from random weights. When we initialize our neural network architectures, we start from random weights. And that, to me, is also not quite as optimal. And what I would love to see is more pre-training, because we've seen that pre-training and sharing knowledge is actually great. And of course, when you dig into the details, there is more complexity. So in computer vision, for instance, we have had a lot of success with pre-training and sharing knowledge with basically an ImageNet pre-trained CNN, or convolutional neural network. And everybody in the vision community got behind this because classification was the blocking task in vision. It doesn't really make sense to go and try to do scene understanding and complex things if you can't even identify a cat versus a dog. And basically with convolutional neural networks pre-trained on a large net, you can now very quickly change just the last softmax classifier just the last layer, and then train and reuse all those weights. And so that has been, I think, a major improvement in computer vision. Now, in NLP, we've had a little bit less success in that we've only so far pre-trained maybe the first or maybe sometimes the second layer, the first 2 layers of a neural network. But then there's still a lot of different architectures that require some memory components and things like that that aren't pre-trained. So we've seen an immense amount of success with Word2Vec, Glove, now context vectors or Cove, and Elmo's Cove pre-training word vectors in context of machine translation, trying to predict a translated sentence. Elmo, instead of predicting the translation, just predicting the next word, but similar ideas there. And those are very exciting, and we see performance improvements, but when you look at the performance improvements, they're all plugged into different kinds of networks. If you want to show that Cove or Elmo worked, then you plug them into one network for classification, another one for question answering, and yet another one for translation, and so on. And basically it shows us also that there's no single blocking task in natural language. There's no single task that everybody in NLP agrees, like, oh, if you can just solve translation, then you will also get, question answering and logical reasoning and so on. And part of that problem, the reason this hasn't happened, is that natural language processing and natural language understanding really require many different types of reasoning. So you need sometimes logical reasoning. If I give you the sentence, 2 people are in the room, 1 person left, how many people are in the room? It's a very logical kind of thing. Sometimes you need to have linguistic reasoning and understand anaphoras, like referring to he, using he to refer to somebody you just mentioned in a previous sentence. Sometimes you need emotional reasoning, visual reasoning, trying to understand the visual world that you talk about, and so on. So there's quite a lot of complexity in language, and language also, unlike vision or in some cases even the outside physical world, you can't really simulate. And so a lot of the algorithms that make great breakthroughs in playing games where you can infinitely simulate your problem domain, you can't really do that in language, because we can't yet generate language in a way that you can have a conversation with it and just have a perfect simulation of that kind of conversation. And so we can't really sample infinitely many times in sort of a conditional kind of simulation way where you interact with that simulator. Of course, we can sample infinitely many sentences, but that's not the point. So language also requires short and long-term memory. And because NLP is so hard, it had essentially, in some ways, almost artificially been divided into these intermediate and separate tasks. And then, once we've had these separate tasks, we could make progress by chasing a variety of different benchmarks, and each of the sub-communities works on their own kind of benchmarks. And so the question now is, like, how do we improve over this? Can we share more weights? How can we do more? And a lot of people think unsupervised learning will solve all of these problems, but I doubt that, because language isn't really unsupervised. If you put a child into the jungle and they grow up by themselves, which is hard, but they will not develop the English language by themselves. You need to actually supervise a lot of skills in language. You need to train it, you need to practice, and get feedback. And of course, some of it you hear because you interact with your parents and other people and so on. But it's clear to me that language requires supervision. If you want to learn to translate, unless you have the luck of growing up bilingually, you really need to practice this. And so all of these kinds of ideas led us to this idea that really, in order to make progress in NLP, what we should be striving for, instead of chasing with particular architecture engineering one benchmark at a time, really what we should do is try to build a single multitask model and have that model get better. And what's interesting is the same kinds of criticism or feedback that I'm getting now about multitask learning was also what I got when I tried to convince the NLP community in 2010 to adopt deep learning for, in replacement of feature learning. People said, well, but I already know how to deal with feature engineering. I already engineered great features for syntactic parsing or sentiment analysis and so on. Why do I need to go back to scratch and ask a model to learn those? Now people say, well, but I know a great architecture for this particular subtask. Why should I go out and try to build this general purpose model that can solve any kind of task coming in? But of course, again, as we become more and more general and we can share more and more weights of these models and ideas, I think we'll make another step towards more general AI and NLP models, and we'll actually get transfer learning capabilities. And I'll show you some of those towards the end of this talk. I also hope, and we have some early results on this, that you'll get more zero-shot learning, where you actually, or almost zero-task learning, where you can do and answer questions or solve NLP problems that you've never seen training data for ahead of time. And the simpler version of that is we'll also want to get domain adaptation, where systems are more robust, even though you've trained it on movie reviews, sentiment, for instance. You want to also identify the sentiment in product reviews. On a more sort of pragmatic side and industry side, it'll also be great if we can have a single model that we can deploy inside companies for a variety of different problems. At Salesforce, for instance, we have 150,000 different companies that are our major customers, and each of them have thousands of seats and employees using our software. So if we had to go in and build a specific architecture for each task, even if we do that like once a week, it will take us 100,000 weeks to really get AI successfully to all our customers. So we always have to think about the meta problems and the meta platform that allows everybody else to solve their own problem. And in general, this is again part of our vision to not just push the state of the art forward, but make it widely accessible. And I think if we have such a multitask model that just solves even complex NLP, so not just classification, but even complex things like question answering or translation in a single model, it'll lower the bar. A lot more people can use it for their own languages, for their own problems and tasks. And in the end, of course, we want models to decide and learn how to transfer knowledge and not say, well, I have one source task and one target task, and I myself will define what kind of knowledge has to be transferred. So the question now is, how do we express all these different NLP tasks in the same framework? So assuming we're on board with having a single architecture and wanting to move forward, we can kind of, I think, divide most NLP tasks into the following three kinds of categories. We have named entity recognition, NER, and aspect-specific sentiment as examples of sequence tagging. We have a sequence of text and you want to give a label to each word. We have a lot of different text classification problems, dialogue state tracking, classifying the sentiment of a tweet or an email or a news article for a stock that you might have and things like that. And we have a whole host of different sequence-to-sequence problems where you have a sequence as an input and you want to generate an output sequence, like machine translation, summarization, question answering. And those three tasks, actually, MT, summarization, question answering, or QA, are actually, I think, three of the most impactful and interesting and challenging tasks in NLP. They're not going to be solved anytime soon in a way that solved means, on any kind of arbitrary text as good as like a bilingual translator. They are, in some cases, a little fuzzy, like summarization is actually quite subjective. Each person probably will benefit from a different kind of summary. Like if you can certain papers, for me, very succinctly. So for instance, you can say Elmo, it's just like Cove, but with language modeling instead of translation as your signal. So to me, that's a great summary, but if you don't know Elmo or Cove, you may have to read the whole papers and the summary would be a lot longer. So those are the three large categories. And so when we're thinking about how to cast everything into a single framework, I had sort of thought of these like 3 equivalent super tasks of NLP. What do I mean by that? Basically, these are tasks that I can see you map every other task in NLP to, and in theory, in the limit, they should suffice. So everything in some ways in NLP is language modeling, and that you're trying to predict the next word in a sequence. And if that sequence is a question, then the next word is basically the answer. And so you want to be able to do language modeling really well. And if you do it, then it should autocomplete every question that you have and predict the next word, which would then be the answer. And we've seen some great results of that already. The problem is a little bit that with that somewhat simplistic view, language modeling doesn't quite work well enough yet on more complex tasks like question answering. So if you take the standard language models and you try to apply them to the SQuAD, the Stanford Question Answering Dataset, or translation, where the prediction is the output in another language, becomes a little harder. So then you have question answering, which I'll get to in a second, and then dialogues. Theory, everything can be cast as a dialogue too. What do you think is the syntactic analysis of the sentence? And then the answer of that is potentially in a dialogue would give you sort of the grammatical analysis spelled out. But the problem is that we don't really have good dialogue data sets right now. So most of the dialogues would be basically one-turn dialogues, and it boils back down to question answering. And so we basically chose question answering. And here is the overview of all the different kinds of questions we want to ask. And it's also kind of interesting sociologically looking at the question answering community. For them, there's very specific types of questions that they think of when they work on question answering. Nobody looks at question answering and would say, like, I want to be able to answer the question, is this sentence positive or negative given this input and this context? Somehow people in question answering don't ask those kinds of questions. They focus on like logical reasoning or extracting facts, things like that. So more like this first one here, where you can basically have a question about a specific Wikipedia paragraph or page, and then you extract the answer as a phrase from that context. So this is kind of the traditional question answering that we've seen a lot of progress being made on SQuAD, the Stanford Question Answering Dataset, for instance. But we want to have that model also be able to translate questions or have translation questions, like what is the translation from English to German? And then the context with most of the planet is ocean water. The answer is the Großteil der Erde ist Meerwasser. So you basically have here a lot of new words, and that's what we show in blue. Blue are words that are generated that didn't come from either the question or the context inputs, and are just newly generated words. And we want to be able to have a question answering system that has that capability. We also want to ask, what is the summary? And then we end up in summarization, where it's a mix. Some words come from context, some words are generated anew. We also, and this is an interesting NLP task, it's called entailment, natural language inference and reasoning. We have a hypothesis, and you want to understand whether it is in a specific entailment, neutral, or contradictory relationship to this premise. In this case, the answer is entailment. Sentiment analysis is its own subcommunity, but really here it can also be cast as a question answering problem. And what's important here is that we actually in the question include what used to be a label or the class, but it's actually just a word and has a word vector like everything else. And that's really crucial because that way you can translate and point eventually to words, even those that you've never seen. So you'll come back to this at the end, this idea of a question pointer, when we can basically answer questions with words that we've never seen at training time before. And there's some really interesting Zeroshot capabilities that fall out of this idea of including the question and the class labels as words in the question. We also have different kinds of other NLP tasks, namely Zeroshot relation extraction, Zeroshot semantic role labeling, dialogue state tracking. Here we translate natural language English questions into SQL instead of into like German or French. It's actually a very interesting idea, and it's one of the tasks that randomly we happen to improve the state of the art on, even though we didn't really keep like that particular task in mind, but our general model that can do all these 10 different things reasonably well can actually do this particularly well and get state of the art. And then here you have Winograd schemas. It's essentially pronoun resolution, trying to understand if Joanne made sure to thank Susan for all the help she had given, then you can ask who had given help, and the answer here is Susan. So essentially, those are our 10 tasks. And when we do this, what that also means is we're essentially zooming out, and we're doing meta-supervised learning. Some people call this meta learning too, and you can kind of see the task embedding here as the question. So T is our task or question, and you basically can observe now that once we include the task into the training data set, now we can also learn more general task embeddings and more general models that, because they have this as an input, they start having layers that are dependent on the kind of task that you have, and it chooses itself how to train and how to optimize so that it does well on different tasks. Instead of having the task T or question usually be outside of the machine learning model, and instead being sort of something that the designer of the algorithms chooses. So this is basically our setup. We have our question, natural language description of the task, T, and that allows the model to use all the different linguistic information to connect these different tasks. So meta-supervised learning, I think, is sort of a way to describe what we're doing here with decaNLP. Now, as we're trying to design this model that can do these 10 different tasks, we had a couple of specifications that we wanted to keep aligned with because we didn't want to have sort of simple cases that don't really get to what we want. So we didn't want to have task-specific modules or parameters where you say, oh, if I'm in the sentiment world, then just run this model. If you essentially, of course, you can say, oh, I have a multitask model that does 10 different tasks. It just has a classifier in the beginning saying, if this task, then run that model. And that doesn't really get us the kinds of transfer capabilities between tasks that we would want. So we wanted to be able to adjust internally to perform these separate tasks so that it gets smarter rather than us getting smarter in how we architecture engineer for each task. And we basically wanted to have that possibility for zero-shot inference on unseen tasks. And so this is the summary of the MQAN model. We call it the MQAN for Multitask Question Answering Network. And also with a little bit of a hat tip to or kudos to Brian McCann, who's the first author of this paper. We basically start here with a context. We ask a question, and then we generate one word at a time. And there are three ways this model can generate a word. It can either point to the context, the input document. It can point to a question, or it can choose a word from an external vocabulary. This is sort of your standard softmax classifier. And we have this pointer switch mechanism that is choosing between these three different options for each output. So let's look a little bit into this model. I encourage you to read the paper, check out the code. It's all on decaNLP.com. It already has over 1,000 stars and hundreds of forks. And I really hope that it will empower you to solve any kind of NLP problem that you can think of. And so let me walk through this model with you on a high level. So we start, and this is kind of similar, I feel like, to Alex Krzyzewski's paper on the first CNN for ImageNet, where they took a lot of the best ideas that have been around and really combine them all into one model. So there's some of that. There's a lot of things that we already know are tried and true and good. That, you know, some of them pretty recent, but then there's some ideas like this question pointer and so on that are a little more novel. So we start with fixed glove pre-trained word vectors. We add character n-gram embeddings to them so that we have vectors even for words that aren't in glove or any other vocabulary, completely new, unseen words. We pipe them through a linear layer, through linear neural net. And then we basically have some shared bidirectional LSTMs with skip connections for both the context and the question. Then we have, similar to Xiong et al., some co-attention mechanisms where we basically want to have different codependent representations now that reinterpret, so to say, the context in light of the current question that we have. And again, we have skip connections, so to have better gradient flow through the network during training time. Then we have additional bi-LSTMs to reduce dimensionality, and then we add 2 transformer layers. And we actually love the transformer. They're very highly parallelizable. It's a great new architecture that builds on some ideas from before, but it's really quite novel and very impressive work. We actually tried to use just transformers for everything, but we could not get that to work. They're still a little finicky. They're not quite as robust as LSTMs in that they just, you know, don't just work. You have to really play around with them, but we were able to make good use of them and have them improve, and we'll show how much very soon. Then we also had this autoregressive decoder that basically uses these fixed glove and character embeddings, pipes them through transformer layers again and LSTM, and then attend over all the outputs of the last 3 layers of the encoder and generate now each word at a time using this switching mechanism between the potential question pointer, the context pointer, and the vocabulary distribution coming from a standard softmax. And together, these are all weighted to combine to the final output distribution, which is 1 word at a time. And we're not even using like fancy things like beam search here yet, which is why some of the numbers are not as high as they could be. It's really just classifying 1 word at a time with these, either pointing them or classifying them. Now, let's go into the evaluation. There is a lot of complexity in trying to properly evaluate how well you do on 10 different tasks. And this was one of the tough things for pre-training and the engineering of this whole project. And we went back and forth. We tried to have a single metric for everything, just like normalized F1 for all the things. But then it kind of makes sense in some cases of why you have blue metrics for MT or rouge metrics for summarization. And we basically decided all of these are technically between 0 to 100. And so we're going to use them as is. And each of the metrics is a little bit flawed. People have shown that sometimes higher blue numbers don't actually result in better like human evaluations of translations, and rouge has its issues and can be a little bit game too. And we had a paper in our group that showed that sometimes better rouge scores don't mean more readable and useful summaries. But in some ways, even though each of the single metrics is flawed, I actually feel like they're a little bit less flawed together, because now you don't have the luxury of just tuning your algorithm for the peculiarities of this particular metric, because you have 10 metrics that you need to care about, 10 different data sets, distributions, and so on. So it actually changes fundamentally how you do your research. Initially, we always thought, oh, we'll just work on just question answering and then see if everything else gets better. And then it doesn't really transfer, not as many of the architectural advances that we make transfer to all these different tasks. And then, of course, you have a variety of other issues like catastrophic interference, and we'll get to that in a bit. So basically, the score that we're defining, because it is good in the end for measuring progress, making actual, measurable progress in a community, to have a clear score and metric. And for us, that is just the sum of all these task-specific metrics. So that means it basically goes from 0 to 1,000 instead of from 0 to 100 for each separate metric. So where are we on this new metric? There's a lot of numbers, but we'll walk through this table. Actually, a lot of interesting tidbits in this table. So first, this whole block here, the first 4 columns, or 5 including dataset names, the first 4 numbers here, number columns, are when each of these models, question answering on Squad, translation on English to German, summarization on CNN Daily Mail, and so on, multi-NLI for this entailment, and contradiction and neutral, classification between 2 sentences. All of these are separately trained. So you can't really compare numbers across here. And what we basically, we'll have a couple of observations, we'll get to it. And then the last 4 columns here are all coming from a single model. So each column here was a single model trained on all 10 tasks combined, and then give any kind of question as input. You might ask, what is the sentiment? The same model pipes it all through our MQAN model. We might ask, what's the summary? What's the translation? Or who's the president of Ethiopia? Lots of different questions you can ask. And it's always going through all the same weights. Everything is shared. Everything is pre-trained, not just the word vector layer, but everything all the way to the decoder and the output. So here we've tried a couple of different models. We actually get one of the reasons this paper is going to be tough to be reviewed is also that people ask, oh, why didn't you use this question answering model as a comparison baseline? And they don't realize that there is not a single model right now in the literature until we publish this that can actually do this reasonably well at all. Like all the Squad models, for instance, all the Stanford question answering dataset trained models only ever point to the context to generate a phrase as a span. So if the answer was, to some context, is this positive or negative, neutral, they would just point to the original sentence somewhere. Or if you ask for translation, they couldn't generate any new words. So their translation performance would be 0. So it actually, it was quite tricky even just to train and optimize the sequence-to-sequence baseline, sort of standard deep LSTM type sequence-to-sequence baseline. Then we added self-attention, these transformer layers, we added co-attention, and we added these question pointers so that you can point not just to the input document, but also to the question. So let's look into some of these numbers and observations that we can make here. So firstly, we can know that transformer layers with the self-attention yield benefits in both the single task and multitask settings. So you get sometimes a whooping like 9, almost 8 or 9% improvements here. Transformer layers helped a lot in question answering and so on. We can also see that if question answering on Squad works well, then question answering as for semantic role labeling also works well. Lots of different kinds of semantic roles that are in this data set that you can ask for. Pointing, this idea of a question pointer mechanism is essential, even for surprisingly things that are just classification tasks. It helped a lot to allow you to point to the word entailment rather than classify the word entailment. In some cases, this is kind of surprising. Multitask learning helped the most for zero-shot kinds of problems. So problems where you don't really never see something at training time, and you still want to classify the kind of relationship. Is this like a teacher-student relationship, or a predator prey kind of relationship, or all kinds of different like broker and customer, like all kinds of different relationships that you might have, and you might only see them for the first time at test time, like certain new kinds of relationships that you see in nature or people and whatnot. And then we also observed that there's still a gap between the combined single task models and the single multitask model that does everything. And we put this here in parentheses because this isn't like a single model. Like even if you had this if clause, sure, you can easily separate between like the WikiSQL task and sentiment analysis with the Stanford Sentiment Tree Bank, but you would have a harder time classifying, for instance, the Zeroshot relation extraction kinds of questions from the squad questions, for instance. And so this is kind of assuming you'd have an oracle that perfectly knows this separate task and now run that particular model. So there's still a gap of about 20 points. And one of the things we've noticed is especially translation, for instance, had suffered a lot in the multitask setting versus the single task setting. Let's look a little bit into training strategies. The default training strategy that we just used before was we basically have a fully joined training where we take a mini batch from each task, focus on the task, and then we go over each of the tasks. And now in the literature, there's been several papers on curriculum learning where the idea was you start with simpler problems and then you go to more and more complex problems as you're during your optimization. And what was surprising, we tried that. So we start with simple tasks like sentiment, just positive, negative, neutral, relatively small data set. And then later on, we go to translation and question answering. And what turned out to be working better was actually opposite of that. This is one of the many, many interesting insights into this first endeavor of really hard multitask learning for different kinds of NLP tasks. And we actually found that it's better to focus in the beginning a little bit on the harder tasks like question answering, like translation. And then once the model had some time doing well on these really hard problems and knowing that it has to stay quite general, then you can allow it to kind of go through different other tasks. You do this round robin, going through and having different mini batches. And that in and of itself was already almost a 9% improvement, closing the gap to the single task model. And I'm confident that soon we'll be able to beat the single task models. It's also in and of itself quite amazing that we have an architecture, even let alone the single model, but we have a single architecture that by itself does quite well. Like in most cases, this isn't state of the art, but in several, in WikiSQL, for instance, this architecture had the state of the art on the WikiSQL dataset, so translating English questions to SQL queries, even though it's a very general model. And model architecture, that is. And so that's kind of fascinating that we can do that now. And if you don't care about multitask learning, you can still use the MQAN model and just train it on your specific task. In fact, you can download the pre-trained MQAN model. And I'm confident that with other researchers joining in and us continuing to work on this, we should be able to close that gap and eventually have a better single task model. And that's probably also a requirement for really the community getting fully behind this. Just like deep learning was great when we can learn features that people took 20 years to discover, but then they had to discover them already. And if you didn't outperform the manually designed features, people had no reason to switch their careers or their techniques to learning those features if the hand-designed features are still better. I think the same thing is true for multitask learning. It'll only really be convincing once we get the great performance on all the things. Now, despite that, I'm already excited about it because there are a couple of interesting things that happen. So here's a little bit of an analysis. The model essentially learned, based on the question, how to generate the outputs. And in some cases, Squad, for instance, is particularly designed to just get phrases from the context. So all the answers in Squad are essentially phrases defined as phrases in the original document. Translation on IWSLT from English to German, of course, there are a few words that are overlapping, like named entities and names of people that you might not want to translate. They're just getting copied over from the context. But then a lot of the words don't exist in either the context or the question. You need to actually generate them from the vocabulary. And there's some interesting ones like Zeroshot relation extraction that actually have a mix. Now, I started in the beginning also talking about pre-training, and this is essentially why I'm so excited about this. Here, we finally move past indeed exciting, but still kind of limited word vector level of pre-training, and we actually pre-train the whole network, including the output layer. And you can also take out different output layers and just pre-train. But a lot of the parts of this model, because of the variety of the 10 different tasks, they're really is quite useful for a lot of other tasks. So here we had two experiments. One was named entity recognition, and another one was English to Czech translation, a different training pair. And we observed that the model that was pre-trained on decaNLP just optimized more quickly and ended up getting better performance than a randomly initialized MQAN model. What's also super fascinating is that the model was quite robust for Zeroshot domain adaptation. So it also got 80% accuracy on Amazon and Yelp reviews, so product reviews and restaurant reviews, even though it had only been trained on 10 different tasks, and one of them included sentiment and reviews of movies. So different domain, but it just worked out of the box. And that's another fun thing for practitioners. If you don't really want to train anything, you just want to get a quick model that does reasonably well on any kind of sentiment, then you can download this and it'll just work to some degree. But of course, you can fine tune it, add more training data from your domain, and it'll get even better. And we saw that with SNLI, where the random baseline is very low. It's like maybe 30 or at most like 50% or so. And without any training on this other natural language inference task, you actually already get much higher than a random accuracy. And when you take, you fine tune it, you add this data set, you still end up being higher than if you were to randomly initialize. Now, this is one of the things I'm most excited about and something I want to continue working on too, and that is Zeroshot domain adaptation, where we basically are able to ask and answer questions that we've never seen before at training time. So here, we really rely on this idea of the question pointer that makes it possible to handle iterations of the question, so different kinds of words, without any additional fine-tuning that's necessary. So we can actually ask, for instance, given the context, John had a party, but no one came and he was all alone, we can ask, is the story happy or sad or happy? And that is quite remarkable. That is able to do classification of stories into labels and categories that it's never seen before at training time. And just a couple of we have a handful of these examples, and it's just phenomenal that it gets this right. And if you want to eventually build chatbots that are more robust than to just the things that you answered, it's actually amazing that we have models now that will be more robust, different ways of formulating questions. And this is kind of Zeroshot classification. Never seen, happy or sad stories, classifying these are 1,000 happy stories, these are 1,000 sad stories, and it'll just kind of work out of the box in some cases, but it's also something we want to test more. So to summarize, basically decaNLP is a new benchmark for generalized natural language processing. The goal is to train the single question answering model. Really, you don't have to formulate it as a question. You can just say, these are commands like translate this into German or something like that. But it's very natural to ask it as a question. In some cases, the question is kind of the same every time. Sentiment is always the same kind of question. In other cases, like squad, the question is actually different each time. And we hope that this is a reasonable step and a framework for tackling some of the really tough, outstanding problems in the field of NLP. Namely, we want to have more general language understanding capabilities. We want to have multitask learning. We want to see transfer learning that naturally emerges by training many different things instead of just having a single source and a single target task, which is a lot of what transfer learning papers have done in the past. We love this idea of weight sharing, pre-training, and potentially fine-tuning for your task, and try to work towards this ImageNet CNN of NLP that really shares a lot more layers than just the word vectors. And in the end, we hope to get to domain adaptation and really cool zero-shot learning capabilities. Now, there's a lot of related work. This is just a tiny subset. It's really hard to do it justice. The original paper has over 100 citations. But these are some of the papers that we really liked and that informed our thinking in the process. And so basically, the idea that we think is reasonable as sort of the next level of NLP is to try to push towards a single multitask model for all of it rather than specific task architecture engineering. I have some questions. All right. Can you explain the attention mechanism used? So basically, it's a lot of outer products. You have the hidden states of the LSTMs, and you just have outer products between them. That's one of the attention mechanisms. And then we call sort of the self-attention mechanism as just a transformer layer. So transformers, multi-head attention, so on. It takes a little bit time to explain and go through. I actually have a lecture on them and slides that really make it a very simple step-by-step comparison on my Stanford class website from earlier this year. So if you go to cs224n.stanford.edu, you can learn all about the transformer type of self-attention. Hey, Richard, you mentioned your repo. Could you provide that link at the end of the talk? I did. It's actually linked on the decaNLP.com website right here. And yeah, right on that website, there's a link to the GitHub repo right at the very top view on GitHub. And yeah, I'll post that link here just in case. There you go. Right. Thanks for the talk. This is very interesting. How would the model generalize to a new task? Could you give an example? Yeah, I guess I did that at the very end. So it generalizes by being able to point to words in the question that it's never seen before. But the reason it can do that is it essentially learned positive and negative are word vectors. They have a certain relationship to the input document that you have. And now there's a certain input relationship to happy or sad. And those are also word vectors. And so it can actually combine those two. All right. Is there a notion of some tasks being more important than others in designing the model? I.e., can the model be incentivized to perform better at task A at the cost of task B? There is absolutely. So one of the ways you can do that is by just training all of them together, and then at the end, just train on the task that you care about for a couple of mini batches and a couple of epochs. That way, it'll just get much better at the expense often of the other tasks, but by you basically care much more one task. And if you care about a task that wasn't in one of the original 10, you can also just take the pre-trained model and only train on your new task. Yes, I sent the organizers a copy of the slides, and they will make them available very soon. Happy to do it, Carlos. Thank you. Yep, there are the slides. This is more speculative. Do you envision that there could be multimodal model, so the same model doing image and NLP tasks, say, of which this multitask NLP would be a special case? I actually do think that's possible. It's something we're also thinking about. That's, again, more engineering, but definitely possible. I think the main issue that we have is that at that point, you kind of have to assume you have a visual module, and you do have a little bit of an if this then that kind of element. But if you are okay with that, saying, okay, if this is a visual task, then look at the outputs of the visual sort of module. I think you can actually reuse some of the higher level layers that get to some rudimentary forms of reasoning with this kind of model. And I think it'll work multimodal too. We actually had a paper already on this for question answering, visual question answering and textual question answering with the dynamic co-attention network, or DCN. I had a paper at ICML maybe a year or two ago, where we had the same architecture doing different things. And once the architecture went over sequences of words, and the other time the architecture went over sequences of neurons from a CNN, each of which, or vectors, each of which describing a particular patch in an image, and then kind of just went snake-shaped over the image and then reasoned over it in a similar fashion to reasoning over multiple sentences. So yeah, I think that could be really cool as well. And my goal, of course, in the end is like, I want to build AI systems that are as general as possible and just work out of the box for as many tasks as possible. All right, in the last minute or so remaining, let's go over Fabrice's question. With such a big network, what are the main tweaks to have a good optimization? Yeah, so it actually took Nitish and Brian a lot of different tries to optimize and come up with the setting that we currently have, the learning rate set to the way they are, and especially this idea of mini batching and anti-curriculum training. So it does. There are a lot of there's a lot of complexity and trial and error as we try this completely new kind of format of learning these 10 different tasks at the same time. And so yeah, it's hard to list all of them, but the ones I just mentioned were sort of the most important and interesting ones, and there are a bunch of other small details, and that's one of the many reasons we put all the code out on GitHub so you can really study some of the details. All right. Well, thanks for the questions. That makes it a lot more entertaining, and since there's some interaction. So thanks, Misam, Fabrice, and others, Carlos. Cool. Bye-bye. Bye, everybody.